Today, we'll be talking about CRTs and CRT TVs. The lesson plan for today is to go over what is a cathode ray tube, who invented the cathode ray tube, the function of a cathode ray tube, the function and the application of a cathode ray tube in a TV, the volts, frequency, and refresh rate, TV specifics such as color, interlace, and fish bowls, and the future of cathode ray tube technology. So, to start off, what is a cathode ray tube? A cathode ray tube is a vacuum tube that is equipped with at least one electron gun. This electron gun shoots a stream of negatively charged particles into the vacuum tube, which is then manipulated using coils that surround the exterior and interior of the tube. These coils emit a magnetic charge, which will in turn manipulate the stream of electrons. These electrons then hit a phosphor screen, which is positively charged, which then allows an image to be displayed. Let's take a look at the diagram below. In the diagram below, we can see many aspects that are labeled. Let's start with the electron gun, where the whole system commences. Electrons are shot out of the electron gun and enter into a tube. In this tube, they are then deflected by both the horizontal and vertical deflection plates. The horizontal deflection plate deflects on the x-axis, and the vertical deflection plate deflects on the y-axis. With these two axes that are being deflected upon, we can make waves, graphs, and much more. It then enters the vacuum tube. The vacuum tube gradually gets bigger, and at the end, it is attached to a luminescent or phosphor screen. When the electrons hit that screen, a positive charge is emitted and photons are converted. When it hits the screen, the luminescent material is lit, and we can see an image that is displayed. So who's behind the cathode ray tube? Who discovered it? Well, this is a very complex answer, as many individuals have built upon this theory and have grown it into bigger and better things. I'll be talking about 3 individuals today. The first scientist we'll be talking about evolved the concept of the cathode ray tube. This individual would be Carl Ferdinand Braun. Braun created the first cathode ray tube oscillator. Before this, cathode ray tubes were characterized as uncontrollable rays. Braun adopted the theory of using a stream of electrons that were manipulated by voltage to produce an image on a fluorescent screen. After this discovery, many more scientists built and further evolved this concept, including both Alan B. Dumont and Alan Archibald Campbell Swinton, the other 2 scientists and physicists that I'll be talking about today. In particular, Dumont evolved commercially used cathode ray tubes for television receivers, and Swinton conceptualized electronic systems found in television sets as well. Both of these aspects play a vital role in CRT TV technology. Now that we have some backstory about a cathode ray tube, how does a cathode ray tube function? The electrons are shot out of the electron gun at an extremely grave speed, averaging 30 million meters per second, which is equivalent to 1/10 the speed of light. The equation used is 2 times 1.6 times 10 to the negative 19 times 3,000 divided by 9 times 10 to the negative 31, all to the power of 1 over 2, which equals to be about 3.3 times 10 to the power of 7, or 33 million meters per second. This equation is essentially 2 times the elementary charge times 3,000 divided by the mass of the electron. As the electrons are shot out of the gun in a steady stream, they enter a vacuum tube. In this tube, the electrons are then deflected using deflection coils that surround both the inside and outside of the vacuum tube, which creates a magnetic field. The deflection coils are made out of copper wire, and there are at least 2 coils, one controlling the x-axis and another controlling the y-axis. Based on the north poles of the coils, we can determine the magnetic field, thus using right-hand rules to determine the force acted upon the electrons. As the particles are electrons, the current is opposite of the velocity. If the electron is shooting out into the screen, then we can determine that the current is going back into the electron gun, or the opposite direction. This magnetic field controls the electron's path and where they're going to make contact with the luminescent phosphor screen. This phosphorus screen refers to a luminescent material and does not contain phosphorus material. When the electrons hit the phosphorus screen, there is a conversion rate of 1 electron to 20 to 200 photons, which will be produced when the electrons hit and interact with the phosphorus screen. As there is a positive charge being emitted through the interaction of the stream of electrons, they are attracted to an anode. An anode then collects and redirects the positive particles, which make cathode ray tubes classified as a closed circuit. In this image, you can see a glowing red light, which is very luminescent. This picture was taken with the lights off. However, this light is very prominent, considering that electrons are completely invisible and naked to the human eye. Where does this light come from? This light is emitted through the speed that the electrons are traveling at and not the actual electrons. Moving on, the video. In this video, we can see a green luminescent light being... Furthermore, in this video, we can see a green light. This green light is going up and down, making wavelengths. These wavelengths are approximately negative values to positive values, back to negative values. This wavelength is affecting the X value. So, based on the screen, we can determine that at least one of the coils is activated, that being the coil that deflects upon the X-axis. As this coil is activated, there's a manipulation to the stream of electrons being emitted through the electron gun, which proves our point of the cathode ray tube. Moreover, as I'm talking about CRT TVs, how does the function of a cathode ray tube apply to that in a TV? In a TV, the same concepts of a cathode ray tube apply, and an extension is present as well. In TVs, different terminology is used. For example, the vacuum tube is often referred to as a picture tube. As a refresher, the vacuum tube is the big tube where the electrons are shot into right before they hit the luminescent screen. Another difference? The coils that surround the stream of electrons is often called a yoke. As a refresher, the coils that emit the deflection is called a yoke. Adding on, in TVs, there's also a need for better sharpness and image quality and resolution. For this reason, more coils may be placed along the X and Y axis as well as diagonally to help in all forms and aspects. In a TV, there's also a refresh rate, as the screen is being used to emit whole images and not solely just graphs and wavelengths. CRT TVs have a standard of 60 frames per second and a minimum refresh rate of 60 Hz. In these images, we can see the cathode ray technology in our CRT TV. The close-up picture is where the electron gun is situated and all the copper wire that is made into deflection coils. As a bigger scale photo, we can also see that the red wire is the positive current as well as the whole cathode ray technology, truly making this a closed circuit. Now let's dive into the logistics and calculations of things. The volts, speed of light, frequency, and refresh rate. To start off, in the 1940s, only 3,000 to 6,000 volts were needed in the final anode. Today, upwards of 25,000 volts are typically used, and this is due to the migration from black and white CRT TVs to colored CRT TVs. The average is around 25,000 volts, however, it can range upwards to 35,000 volts. But as there's such high voltage, there's only a few milliamps used in a CRT TV. I would like to stress that the electrons being emitted by the electron gun are at crazy speeds. As I mentioned before, approximately 1/10 the speed of light. In my opinion, absolutely crazy. There's a theory that 0.25 minuscule c is the typical acceleration for approximately 17,000 volts, and minuscule c stands for the speed of light in a vacuum tube. In other words, perfect for a cathode ray tube as there's a vacuum tube. So using that theory, Dividing 0.25 by 17,000 gives us approximately 1 over 68,000. I took 1 over 68,000 and times it by the average volts, which is 25,000, and that gave me a result of 0.37 C. I also took that same number, 1 over 68,000, and times it by 35,000 volts, which gave me 0.51 minuscule C. So the average speed is approximately 0.37 C with a low of 0.25 C, which equates to 17,000 volts, and highs of 0.51 C, which is a high of 35,000 volts, which I'm assuming 35,000 volts is for a colored CRT with a higher resolution, with more deflection coils, basically a higher quality image, and 17,000 volts is more so for a lower quality CRT, or an older one for that matter. I also carried on and did this equation for black and whites CRT TVs. As mentioned previously, in the early 1940s, there's only 3,000 to 6,000 volts used. So 3,000 times 1 divided by 68,000 equates to 0.0444 minuscule C. And for a high of black and white TVs in the 1940s would be 6,000 times 1 over 68,000, which equates to 0.088 C. Finally, let's take a look into our final equation. It is standard to have 60 frames per second on a CRT TV, with a minimum refresh rate of 60 Hz. The equation for the refresh rate from the horizontal scan lines, meaning how many horizontal scans are used in a second, the equation for that is the scanning frequency divided by the number of horizontal lines on that TV times 1.05. And the reason why we use 1.05 is because it takes about 5% of the time for the electrons to go from top to bottom, meaning vertically. It takes 5% of the time. That is why we times it by 1.05. The number of horizontal lines really depends on the TV you're going to be using. For example, a monitor with a horizontal scanning frequency of 96 kilohertz at a resolution of 1280 times 1024 results in a refresh rate of 96,000, which is the hertz, divided by 1024, which is the horizontal lines of the TV, times 1.05, equates to 89 hertz, rounded down. This is also assuming that the horizontal lines match the dimensions of the TV at a 1-to-1 ratio. So the average rate for this would be 89 hertz rounded down. And 89 hertz essentially means 89 full screens of line per second, meaning that the electron is going to go from the left side of the screen to the right side and back 89 times per second for one line of screening on the TV. Now, moving on, the average refresh rate is 60, 75, and 85 hertz, but can be upwards of 100 hertz. So in order to get the average, we would times 60, 75, or 80, doesn't really matter, depends on the TV, times the dimension of the TV that you're going to be analyzing, times 1.05. And using this equation, we can get the scanning frequency. Now moving on to the niche of things, TV specifics, colors, interlace, and fishbowl. Let's start off with colors. Colors in a TV is an extension to the standard black and white TVs. Moreover, color TVs are based on red, green, and blue. With these three main colors, there are 3 electron guns emitting electrons into 3 different colored phosphor screens. In other words, the same core concept as black and white, but just 3 electron guns as well as 3 screens, 3 times the original amount. As these colors are emitted, there's also an additional component that would be the volts that these electrons are shot out at. The higher the voltage, the more vibrant the color. Meaning, for example, if I wanted the TV screen to be purple, I would shoot equal volts of red and blue to create this color. If less of a base color is needed, a lower voltage will be emitted. Another concept would be interlace, which is a concept that interlaces the images. As I mentioned before, there are 60 frames per second, but only 30 total pictures or images. The pictures are divided horizontally into odds and evens, like this image below. Odd field and even field equal the complete frame. The odds are shown first, and then in the second frame, the evens are shown. Because the electrons are moving so fast, to the human eye, you will not see much of a difference. However, this does save in a lot of electricity for the TV. Into a final concept, the fishbowl, my favorite. The fishbowl is also common to see on TV screens on the exterior, meaning it is a curved shape and not a flat screen. As the electrons are being reflected, the radius and the finish of the electrons are quite different. In this video, you can actually see, as I bring my phone closer and closer to the TV screen, the red, green, and blue that are emitted onto the TV screen. Moving on to our final concept, the fishbowl screen. Have you ever walked and seen an old TV and see the bulge on the exterior of the screen? That is exactly what I'm talking about. The fishbowl is very common to see on old TVs as the electrons are reflected and reflection creates an end result of a curved finish. Samsung actually changed the game by adding glass on the interior that would make the exterior look flat. However, the interior is still the same curved, and the technology used is more of a refraction to make the exterior look flat to the human eye. There's also an electronically modified curve to ensure the image would still appear in focus and clear. As I'm showing a walkthrough of essentially this CRT TV, I figured that my CRT TV that I have at home is actually a flat screen, and if you look very closely, you can kind of see the fishbowl on the interior of the screen. Ending off, let's talk about the future of cathode ray tubes and cathode ray tube technologies. Although many CRT applications are coming to an end, for example, the oscillator that I've been showing around is double my age. Keep in mind, I'm 16 years of age. CRT TVs are also being eliminated by their LED and OLED competition. The core concept of cathode ray tubes, however, is still evolving and changing the future. The concept that a stream of energy can be deflected and emit an image is still being evolved and used in our modern day era. A big example of this extension is our lasers and photonics. These examples are light sources that are used in displays, imaging, and also new technologies such as LASIK surgery. In these concepts, a mirror is used to deflect and bend the light to suit the need for energy. In other words, and simpler terms, the same principal concepts of cathode ray tubes, using outside tools to manipulate a source of energy. Even though cathode ray tubes are diminishing and coming to an end, there's still a need for this main core concept in our evolving modern day era, which is something that I would love to see and love to learn about, as I truly do think that cathode ray tubes are always going to be in our future, as it is such a simple concept that is always going to be used. Now it's going to be used in lasers and photonics. In 30 to 40 years, I still think it's going to be extremely relevant to the STEM field as well as our modern day world. Thank you for listening to my explanation of CRT technology as well as CRT TVs. I hope you have a wonderful rest of your day, and I was extremely joyful to have learned about this whole process, as it is something that I'm actually extremely passionate about, as it is such a simple but relevant concept.